Again, good morning everyone. To start the program, I would like to introduce the Director of the Electrical Electronics Engineering Institute, Dr. John Richard Wilson.
Hello. Hi. Good morning, everyone. A pleasant morning. So today marks a special milestone for the PCARI as we open our doors to our partners in government, industry, and academia for this very interesting seminar on resilient electricity grids. This topic is an important one for our industry as we look at ways on how we introduce innovation into this particular sector. So our situation in the Philippines is quite unique, being an archipelago of 7,000 islands. Having that resource, the renewable energy, the potential for that, and also having a limited infrastructure that allows us to harness this particular energy. So our institute is optimistic that we, as a country, can develop these technological solutions. And with everyone present in this seminar, I think we're stepping in the right direction. Our institute is committed to serve this country through our research and extension, and we seek partners in government, industry, and academia so we can have that impact and really make a difference. So we would like to thank CHED and the support that PCARI has given us in helping us achieve this mission. To our partners in UC Berkeley, Sasha, her team, this collaboration has helped us to reach out, and hopefully this technology will be adopted in the country through our distribution utilities, and the know-how can also be reintroduced to our curricula through our partner universities. As a final note, we are always looking for collaborations here at the Institute to address the societal problems of our country, and our doors are always open to those who wish to partner with us. And we are keen to help, and we are always open for collaborations, like I said, and may we have a very fruitful discussion throughout this seminar. Thank you very much.
Thank you very much, Richard, for the encouraging opening remarks. Well, to start the program, I will be giving an overview of the seminar, what to expect the entire day. So, well, I'll use the next few minutes to give you an introduction on PCARI. You've seen the word PCARI over there, you've heard it. I mentioned it before and Richard has mentioned it. I'll tell you a little bit about PCARI and then tell you about a little bit about the sessions that's going to happen this afternoon and how it is connected to the project. Okay, so, well, to start, PCARI means Philippine-California Advanced Research Institute. It is a research program that is funded by the Philippine government through the Commission on Higher Education. So several years ago, around 5 or 6 years ago, Dr. Dado Banatao of the UC, University of California, well, he approached the Philippine government so that the government and the academia would come up with something so that we will progress technologically. And one of the solutions that was brought up was to partner with other universities, in particular in this case the University of California system. And PCARI is again Philippines-California Advanced Research Institute, and under the PCARI system there are two institutes. The first one is what we call the IIID. IIID is Institute for Information Infrastructure Development, and the second one is IHITM, which is Institute for Health Innovation and Translational Medicine. So the project right now, Resilient Electricity Grids, belong to the first one, the IIID. Well, for the second one, IHITM, they're working more on the health sciences. So for the IIID, universities in the Philippines like UP Diliman, Ateneo de Manila University, and National University partnered with some of the campuses in University of California, in particular Berkeley and Davis. and to jointly pursue research projects. So there are, this project, Regenerative Grids, belong to the second batch of projects approved by PCARI. And right now, I think there is a call for the fifth batch of projects for PCARI, and that will be, I think, due in a couple of months. Well, the objective of PCARI is to develop solutions, in this case, information infrastructure. And not only that we have to develop solutions, but we have to show that these solutions will work for us, will work for the Filipino people. Okay? And that's why we are working with Sasha and Thomas and Charles, well, in this particular sector, power engineering, to help, okay, to help address our energy problems. So, the project PCARI IID 2015-10 Resilient Electricity Grids actually has 3 component projects, and you will hear more about that later on. Sasha will talk about it. But I'll just give you a quick overview on what those projects are about. So the first project works on interruptible load program, and the main objective there is to design contracting frameworks on how we can tap at the demand side to address our energy supply problems. So those from the electrical operatives, you have already heard the interruptible load program. What we want to achieve in this study is, well, to come up with a more efficient way of getting the demand side involved in the system. Okay? Now the second part is on instrumentation of the distribution network, and later on Sasha will talk about the micro-PMU technology. Micro-PMU, again, these are sensors deployed in the distribution networks, measures voltages and currents. Basically, it gathers information in the network, and it will help us understand what's happening in the network. It would help us make operational and investment decisions. And the third component project is on energy analytics. So we are putting instrumentation sensors in the network. We are gathering a lot of data from the network. Maybe it will come from the substation or from the transformers or the distribution network itself. But we don't have to stop from gathering data. We have to make sense of that data, and this is where analytics comes in. And here we are borrowing techniques from machine learning to understand what's going on in the network, given, say, a few measurements that we have. So I have mentioned 3 projects, and we have 3 sessions devoted for each project. So this morning we will have a session on Microsynchrophasors for electricity distribution networks, and that will be taken care of by Sasha. And Jordan will be chairing that session. And working with Sasha is Thomas from Power Standards Laboratory. And then we will have lunch upstairs. So the lunch will happen, go up the stairs here, and it's at the far end of the hall. So we allocated three rooms so we could have our lunch. Unfortunately, we didn't put time for snacks this morning because we started relatively late. And then in the afternoon, we will start at 1:10, and Claire Tomlin, unfortunately, she cannot join us today, but she will be joining us through Skype, and she has sent a presentation, and we will hear her about their work on demand-side management, designing of contracting frameworks for demand-side management. By the way, the afternoon session will be chaired by me. Okay? And after Claire, there are 3 more speakers. Dr. Alan Nerves, also from the EEI. And actually, he is presenting on behalf of one of our master students who is unfortunately away right now on his work on incentive design for commercial industrial loads. And then we have Audie speaking after him. We're fortunate to have Audie with us because Audie is part of another PCARI project, and Audie is working with Anil Aswani in UC Berkeley. And then lastly, we have another professor from UP-EEI, Dr. Nestor Tiglao. He's at the back right now, and he will talk about transactive energy. And then after the second session, we will have a short break for some snacks and coffee. After that, we will have the third session on analytics, and Alan will be chairing that session. And we have four presentations. Aziz, Anton, Ethel, and Christian. They are masters and PhD students working in the project. Now, our objective in this project or in this seminar is, well, firstly to highlight and introduce to decision makers what we are doing. That's why we have invited personnel from the government, from the Department of Energy, from PCARI itself, INEA, from the Distribution Management Committee. We also invited personnel in the academe, so from different universities like Pua, PIP, Quezon City, Manila, TUP, PUP, UPLB, a couple of universities, Pangasinan State and Cavite State. I'm not sure if they are around already, so I hope they can join us. If they're not yet here, we have also invited people from the connected with electric cooperatives and distribution utilities. So we have guests from the Corp, Meralco, Batelec, Beneco, and Iseco. And also joining us today are researchers within the university community. Okay, so later on we will also talk about, well, Richard mentioned about collaboration. Right now, the Corp is here with us, joining us because, well, they are, at the moment, our partner electric utility. So, the technologies that will be discussed this morning will be rolled out or implemented using their network. And, well, I am saying that because we want these technologies to be adopted by the Philippines. That's why people from the government and the academy and the cooperatives are here. We want to convince you that, well, we are convinced that we are developing solutions that can help us. But it doesn't stop there. We have to convince everyone that we have answers to some of our problems. We're not claiming that we can answer a lot of problems, but we have solutions to some of our problems. And I would like to request your entire day to hear us out, and then later on, we can decide that this day is just the start, okay? And hopefully that we can also use this event to reach out to the other universities and to the electric cooperatives and to the government. Okay. So before I turn over the microphone to Dr. Jordan Orellasa, I'll just go through some safety procedures. Well, we have a couple of doors, just in case of emergency, so let's not panic, let's just calmly walk out if something unfortunate happens. We have, when you enter through the ramp, but we have the door that opens outside, and in case of a fire or emergency, the assembly area is the parking lot right here in front. So with that, again, I would like to welcome everyone and trust that we're going to have a productive and an educational day ahead of us. Maraming salamat. So to continue, sorry, I'd like to introduce Dr. Jordan Orellasa, and yeah, actually I forgot to mention that there are 3 research projects comprising the program. And the first project, the one on interruptible loads, is led by Dr. Alan Nerves. The second one is led by Jordan, Dr. Orellasa, and I am leading the third research project. And the 3 of us are affiliated with the Electrical Electronics Engineering Institute. So Jordan?
Magandang umaga po sa mga lahat and good morning to our guest this morning. So for the next 2 hours, as Mike mentioned in the morning session, I will actually have 2 speakers. The first one is Sasha, Alexandra von Meier. She is an adjunct professor at UC Berkeley, Electrical Engineering Computer Science. She's also the director for electric grid research at the California Institute for Energy and Environment. We sometimes refer to it as CIEE. I think many of you will recognize her as the author of the book, Electric Power System, A Conceptual Introduction. This is published by Wiley, available with IEEE. I personally highly recommend that book, even before I met her. This is really good, both for engineers and non-engineers. If you look at Amazon, it's rated 4.8 right now, with a few hundred reviews. It's still a good book, but basically we're privileged to hear her out this morning. She's a good speaker, good teacher, and a good writer as well. We're privileged to work with her in this project, and we're so pleased that she came over all the way from California, even with some travel ban from the US. She still made it here. Together with her this morning is actually Thomas Pua. Sasha will introduce him more in the middle of the presentation. I know him basically as one of the people who worked in the development of the micro PNUs. So they were part of the project. It was part of a project funded by ARPA-E, the Department of Energy in the US, who developed this ultra-precision, high-resolution meters for voltage, magnitude, and angle measurement. So again, we're very privileged to have them here with us this morning. So as per our schedule, it's 9:30 right now. They will be together. They will be taking the floor for about 2 hours. And then around 11:30, we'll have an open forum before we have our lunch at 12 o'clock. So again, join me in welcoming Sasha and Thomas.
Thank you, Jordan. That was such a nice introduction. I'm really happy to be here. Thank you so much for having us. And I don't know what your custom is in terms of interrupting speakers and asking questions. I want you to invite you to do that because I'm not entirely certain. Let me see a show of hands. How many people here have a power engineering background? Okay, so not everybody. And let me tell you why I wrote a textbook on power engineering, because I didn't have a power engineering background and I found it to be really difficult to learn and understand. And so I started to write the book that I wished I could have found to explain to me what the heck is going on. So please don't hesitate to stop me. What I would like to do this morning, most important, is to make the case for why high precision measurement is important, and then go into some of the examples of what we can do with the high precision, high resolution data, and transition to telling you about some of our research adventures, both at UC Berkeley and here at the University of the Philippines. I also want to say just how fortunate we feel, speak for my entire team at Berkeley, when I say we feel so fortunate to be working with this team here from UPD, because Jordan, Mike, and Alan have been wonderful collaborators, and all the students have been really great. So it's a great pleasure. I am not going to go to the keyboard assistant. No, we're going to go to slide 2, and we'll figure out how to make that happen. Slide 2 tells you my favorite quote about electric grids. Yeah, there we go. It's a system that works in practice, but not in theory. Yes. And you know, the more you learn about how electric grids actually work, the more you're amazed that the lights are on at all, ever. Because there's so many things that have to go right for it to work, and then you think about the fact that that this is a system built on technology that's not even 20th century technology, it's 19th century technology. How do they make it work? Well, let me start by saying it's not only old, it's also complex. There are so many different diverse parts that have to work together. And a definition of complexity that I like is that it's a system that no single entity can account for at any one time. Not a human or a machine can actually know everything that is relevant. It can account for every variable that is interacting within the network of an electric grid. It's also difficult to observe because electrical phenomena are really abstract. You can't see what's happening inside a piece of copper or aluminum, so it is not intuitive, and it is hard for an operator to actually have a good real-time sense of what is happening, what are the tensions, the dynamics inside the system. And oftentimes you don't see it until something breaks and the lights go out. Now, the way I think about the fact that operators have been successful at all in operating the electric grid is in terms of survival strategies, design principles that were built into the electric grid from the beginning. And it starts out with the fact that there is actually quite a bit of energy storage in the grid. Sometimes you hear people say, well, power has to be produced and consumed at this, of course, is true. And they say there's no storage in the grid. That's not technically true. There's very little, historically, very little storage because it's expensive. Batteries have been very expensive. Pumped hydroelectric storage is an example of a technology that is inexpensive and it works well, but you have to have mountains and water to make it work. Not everywhere do you have that privilege. But there is actually a really important amount of storage, well, first of all, in fuel. Fossil fuels inherently are energy storage that we forget about, but in those can't really see it against the lit screen. But you know, in those containers, that's oil waiting to be burned. There's also the rotational inertia of large machines, which actually plays a very important role on the small time scale of stability for an alternating current electric grid, without which we really wouldn't be able to maintain synchronicity among all the machines. So there is actually stored kinetic energy that adds up to pretty significant numbers that creates, it goes to the third point, creates an inherent stability as well, because the generators interact with each other, and if one starts to move faster than the others, it encounters more force pushing back on it, which will tend to slow it down. So that inherent feedback is built in to the rotating machines that have been the workhorses of this industry. There's redundancy built into the system because we don't know exactly how much capacity we're going to need at any given time. So the traditional approach is we build extra, we make it larger than we think we're going to need because we don't have perfect information. We build extra transmission links, we have extra power plants standing by for generation. And then finally, what has made it possible to operate distribution systems in the past is that they're quite simple in the architecture. It's a one-way radial design, power flows from the substation in the direction toward the customers, and there's not too much head-scratching or analysis that has to happen. If you build it large enough to handle the peak load condition, then you pretty much know it will always be large enough. Now, what I call survival strategies are becoming outdated. They aren't going to work forever because, for one thing, the big rotating machines are being replaced with newer technologies, inverters, wind power, solar power that's not directly dispatchable, and that has new opportunities for being controlled, but it's going to require a different level of insight and fine-grained control. There is also now more economic pressure than there has been in past decades to not just oversize everything. We want to make electricity affordable. We are also wanting to place generation resources not just in central locations, as we have done historically, but at the periphery of the grid, on customer rooftops, in many diverse places where they connect to the distribution system, not just to the transmission system. And then finally, we have smarter loads, smarter customer resources that can be responsive and intelligent and help provide a lever of control that was not historically available. To recruit those resources, we have to be able to see what they're doing. We have to see what is going on in terms of the actual power flow on the electric network in real time. We need that to support the integration of solar and wind resources. We need that to be able to give the correct signals to customer-owned or other third-party resources on the grid to tell them what they should be doing right now that would be helpful to make them good citizens on the electric grid. If they are not behaving in coordination, they can create significant electric problems. If they are behaving in a well-coordinated manner, they can solve many of the problems of the grid. But again, for that, we need insight and information. And really what we want to do is we want to maintain reliability and resilience for the grid so that we can continue to enjoy lights that stay on most of the time, and also have a grid that can recover from disturbances when they happen. Because the word resilience is in the title of our research project, I think it's worth trying to define it. To me, there's an important distinction between reliability and resilience. And, you know, the visual aid here is like the bamboo, which is flexible and it bends, but it doesn't break easily, as compared to maybe an oak tree that has very strong wood, but once you break it, it's broken, right? And so resilience is like the bamboo. It bends and it flexes and it bounces back, and before you know it, more bamboo shoots have grown out of the ground. It's about responding to new and changing situations. It's about recovering from disturbances when they happen, not even necessarily being able to prevent the disturbances, but having a action that you can take in response and mitigate the impacts of challenges to the system. So resilience is very much a dynamic property, and that's why it's a research project, because it depends on developing greater visibility and intelligence and flexibility of control actions where maybe in the past we haven't been controlling things. So that's kind of the motivation for our 3 joint projects that Mike and Jordan introduced. Altogether, they really, I see them as 3 parts, 3 legs of a stool, if you want to say, 3 parts of an overarching project that's about new methods for flexible, resilient, efficient networks, particularly focusing at the smaller scale at the periphery of the network, so involving customers, distribution, local distribution circuits, and making them ready for what we believe is going to be a growing contribution from distributed resources. We have the 3 projects labeled. Project 1 focusing on customer loads or demand side management, Project 2 the sensor part of it, and 3 the analytics. We're really, what I love about this project is that it's not really an abstract academic exercise. We're very much focused on getting practical results and very much focused on developing techniques that can be used in the field in practice right away, because we want to have an impact immediately. So this is the outcomes we hope for and expect are increased reliability, improving the efficiency of operation for the utility companies, and again, increasing the range of options for the grid to respond. So these 3 pieces, I'm putting observability first, intelligent algorithms, that is for making sense of the sensor data. That's a diagnostic component. And then another is control, that is controlling diverse resources, and again that requires intelligent algorithms to make use of sensor data and information to then issue good suggestions or commands. All three of these take advantage of new types of data and tools, and the physical measurement data are a very important piece of this. I'm going to skip this slide because it's basically a restatement of what I've already told you, except to say that I'm going to start in the middle with Project 2, because Professor Claire Tomlin, after lunch, will be focusing more on Project 1 and say more to the demand-side management. And logically, it also makes sense to start with the physical sensor network. So I will speak about the microphasor measurement units, or PMUs, and then begin to talk about the data analytics. So observability is actually underappreciated as a sort of a scarce property of power networks. Many people think of, and I don't have a picture here, of transmission system control operators where they have big screens full of data. We're beginning to get some of that at the more local distribution level, but much of the operation still is more similar to that upper picture, which is in California not so many years ago, where the distribution operator basically is referring to some paper maps, and his main mode of communication and eyes and ears in the field is just talking to one of the line people who are out. If he wants to know, that's Andy. If Andy wants to know what's going on, he picks up the phone and talks to someone on the truck to drive out there and look what's happening. And there are a lot of electrical measurements that basically can't be seen. So the objectives of this project in practice are to actually deploy, roll out a pilot project of high precision instrumentation, and we have secured the interest and collaboration of a Philippine utility that I'm very much looking forward to visiting and talk about the technical details of how these units will be installed. And then these data from the sensor network will be used for advanced algorithms that students at UC Berkeley and here at UP Diliman are working on to convert what are just abstract sensor data into usable, actionable intelligence for the system. So the sensor network that we developed at UC Berkeley is kind of a model that it was funded by the United States Department of Energy in the good old days when they still thought that promoting renewable energy was a good idea. We hope to return to those good old days. The idea is that we put instrumentation behind the substation. So the electrical substation is where power is being converted from high to medium voltage. Usually at the high voltage side, at the transmission level, it is common to have fairly good measurements because there's a lot of money involved and there's a big risk to reliability if something goes wrong at the high voltage level. But beyond the substation, when you get into the neighborhoods, there's typically very little measurement, and until you get to customer meters, which also have pretty low resolution, low quality data. So the idea is that we take the state-of-the-art, the best kinds of electrical sensors we can get and spread them out on the actual distribution circuits. And we don't just measure voltage and current magnitudes, but we measure actual synchrophasors. Now, raise your hand if you're familiar with synchrophasors, because I don't expect that people are familiar. So I will take some time to do that, and that's probably the most important piece of my presentation, because without sort of seeing the importance of the synchrophasors, much of the effort doesn't really make sense, or you don't really get the feeling of why this is special, or why the algorithms are special. So we start out with an alternating current, voltage and current, and that's a sine wave, right? And we're familiar with the notion that it has a magnitude, or an amplitude, or a root mean square value for its height that measures basically, how much voltage or current do we have. But there's another property, which is the phase shift in time, that to a first approximation, usually we ignore when we talk about a synchronous AC network. To a first approximation, we imagine that the voltage goes 0 to maximum, to 0 to maximum negative, and back around, all at the same time, because that would be synchronous. In reality, there's a time shift between any two locations on an electric AC network when that voltage crosses the 0. And that little amount of phase shift here is labeled with the delta. So that phase angle is actually a really important measure. It's a fundamental physical state variable. It's a driver, a fundamental driver of power flow through the AC network. And a device that can measure that is a device that has to have a really good clock. Not only does it need a really good clock on board, but it needs to use the same clock as a measurement device at some other location, because they have to compare their measurements to each other. So it was really GPS timestamping that made the phasor measurement unit technology feasible and practical, right? So when we say a phasor, we're talking about a quantity that power engineers are familiar with, an abstraction, a complex number that has magnitude and angle. The PMU is the phasor measurement unit. That's the hardware that can actually measure both parts, the real and imaginary, or the magnitude and angle part of that phasor. Then a micro PMU is a device that is specifically tailored to distribution systems where the measurements they have to make are smaller. And so it has to make a more precise measurement, but also at the same time deal with more noise. So that is quite a different kind of machine that you have to build to do that well. The word synchrophasor refers really to the data output from the PMUs, and sometimes people use the terms interchangeably. The graph with the logarithmic timescale just illustrates the precision that we need. It's really a timestamp that's better than a microsecond. It has really nanosecond precision, sub-microsecond accuracy when you're comparing measurements from two locations at some distance apart. So these phasor measurement units became popular. They've become popular all around the world. In the United States, really it didn't take off until after 2003, when we had a big blackout that made big news, and people said, oh wait, we should probably check out these new devices and install them. GPS technology, like I said, is crucial, and it allows us to observe directly the voltage magnitudes and angles at different locations, which, as I've said, are physically what's driving power flow. So you can visualize it in a very straightforward way if you think about two rotating machines, two electrical generators at different locations. One of them has a rotor angle that's a little bit ahead of the other. They're rotating at the same frequency, so they are synchronous, they're locked together, but one's just a little bit ahead. If you play music, you can think of it as, two people in a band who are playing in the same rhythm, but one is anticipating the note just a little ahead of the other. And so that delta difference can be approximated, approximately related to the real power flow between those 2 points. In transmission system, that's a pretty nice and easy relationship. It involves the two voltage magnitudes and x, the inductive reactance between the two locations, and then the sign of that angle difference. So if anytime there's AC power flowing through a line, a conductor, there is going to be a difference between the voltage magnitudes and angles at the two locations, and that is what we're about to measure. When we measure this is an example of a map produced by colleagues at the University of Tennessee for the eastern United States. You get illustrates a visual sense of what you might call a heat map of voltage phase angles being associated with more power generation, that is, the generators that are slightly ahead, they're pushing harder, injecting more power into the system, and those are located in the red areas where a lot of power is being injected, and then the areas that are darker blue, in particular New York, for example, are areas that are lagging behind an angle where there's more power consumption. So power in this diagram is flowing from red to blue. These are very, very large angle separations, and it's amazing that that is even stable. The only reason it's stable is because in between these places are a lot of nodes where there's generators injecting power and maintaining the stability along the way. These numbers from minus 50 to plus 50 degrees are also much bigger than what you would see in a distribution system. So until we started this DOE-funded research project in 2013, nobody had really done synchrophasors or PMUs at the distribution level. And there were good reasons for them not to. And some of my friends and colleagues looked at me like, are you a little crazy? Like, why would you want to do that? In fact, when I started writing the proposal, the research proposal, I asked two colleagues, do you think there's like hope for distribution synchrophasors? And both of them were like, nah, They're like, well, I just have this intuition it might work, and I wrote the proposal anyway. And then some people at the Department of Energy thought that, well, this could be a really good idea. And so we went for it, and as I'll hope to persuade you, there's actually some really cool stuff to see. But there was good reason for nobody else to have done this. First of all, because historically, like we said, distribution systems are pretty boring. It's one-way power flow, and it's radial, and there's just not a lot of science to do there. But that's changing. We want to control things, we want to recruit resources on those systems. Also, if you want to economically deploy a network of sensors and distribution, they had better not be too expensive, right? And the transmission PMUs, last time I checked, they were still like about $20,000 US a piece, which is just more than you can afford to deploy in the distribution setting, because there's not that much connected load, not that much energy to justify that investment. So we have to get down to a much lower price point. But then the big reason is that making the measurements and drawing conclusions from the measurements at the distribution level is much harder. You have to have a better device, and you probably have to scratch your head harder when you're reading the data to see what it's telling you. The performance of transmission PMUs is conventionally described in terms of a total vector error, which is basically, in the complex plane, the radius of that red circle that says, well, if you measure the voltage phasor, you're going to get it to within some distance, right? And it could be a magnitude error or a phase angle or time error. So in transmission, if your PMU is within 1%, or 0.01 per unit of the magnitude of that whole phasor, then you're okay. Then you're meeting the standards and the expectations. Well, in distribution systems, 1% is not good enough. It's not going to tell you anything, because you're looking for differences between two nodes in the network that might be smaller than that amount of error. In fact, if you translate the 1% of total vector error into a number of degrees, we get 0.6 degrees, and that may be bigger than your signal, which could be a small fraction of degrees. Now, if you're not a power engineer, you may avert your gaze, and you don't have to look at this. But if you are a power engineer, you'll appreciate the fact that what I've crossed out and read, the transmission system approximation, is no longer good when we're dealing with distribution systems. And the primary reason it's no longer good is because the transmission system approximation insists that the magnetic inductance, or the inductive reactance X, is primarily what's physically characterizing that conductor. It has a little bit of resistance always, but unless you're calculating losses, you don't really care. The resistance is not really indicative of the power flow in transmission. But that's because you're dealing with big fat wires that are spaced a big distance apart. When you're thinking about, when you consider wires that are skinnier and closer together, then the magnetic inductance effect becomes less important and the resistive effect becomes more important. So the resistance to reactance, or R over X or X over R ratio in the distribution system is much more tilted toward the resistance. That makes that approximation not work well. Our team has worked on linear approximations that would relate voltage magnitude and phase angle on the one hand to real and reactive power P and Q on the other hand, because we know we need a linear relationship to ever be able to run control systems, control algorithms. So we've come up with those approximations that are probably pretty good a lot of the time, but they're much messier than what you see up there. So you have to account for resistance and reactance at the same time, and you have to account for real and reactive power at the same time. You can't decouple them like you can in transmission. And then there's another problem, and we're not going to get into it, which is that you have three phases which are not the same. They're not balanced like they are in transmission systems. So that means actually all of these quantities turn into 3x3 matrices, which I can't even deal with. I have my PhD students deal with it. I can't handle it. But so a summary of what makes distribution synchrophasors really hard is that we are looking at small voltage phase angle differences. There is, at the same time, much more noise in the measurements because all sorts of stuff is going on that may or may not be important to what it is you're trying to determine. As I said, we have the different X over R ratios, so you can't use the familiar approximations. You have unbalanced three-phase systems, which means that phases A, B, and do you call them A, B, and C here? They don't have the same load. They also don't have exactly the same impedance, right? So finally, you get to the network models, and this is my pet peeve. A lot of academic papers, including some papers by students, assume that we can rely on the model of a circuit and then draw intelligent conclusions from that. Well, if you talk to someone in an actual utility company who deals with distribution circuits, and you ask them for a circuit model, they say, of course we have a circuit model. And then you start to talk about, well, how good, what is the fidelity of that model? How closely does it resemble to what is physically out there installed in the street? And then you sort of shrug your shoulders and you say, well, it might be pretty good in some places, but oftentimes the kind of mathematical accuracy that we imagine we're dealing with when we write academic papers has nothing to do with the fidelity of a model in the real world, where who knows, The guy who was installing the conductor out in the field, maybe they ran out of some size of wire, so they used a different size wire, you know. That's not captured in the database. There's any number of things that could happen in the real world. You have underground cables. The model makes an assumption about how those cables are configured. What's the geometry? Because the magnetic field is different, right? Well, the way that they actually put the cable in the trench may be nothing like what it says on the paperwork, right? So what's actually a really interesting science problem is how do we get good information and make good decisions in the absence of high fidelity models? Or how can we use the empirical measurement data to improve our models and update them and validate them? You know, like I say to my students, rule one, all models are wrong. And that's true for every model of everything, because a model is not, the map is not the territory, right? But the question is, how informative is it for what it is that you're trying to do? So finally, we get to the problem that a distribution network has many nodes. Basically, every service transformer is a node, and we're not going to put a high precision sensor on every one. So we have a small number of measurement points compared to the nodes in the network. That makes it, first of all, impossible to do what in transmission analysis you call a state estimation, right? You don't have as much input, but there are creative ways around that, some of which you'll hear about today. And then finally, it's not always easy to gain access, whether that's for technical reasons or reasons of privacy and security. It's not always easy to combine all the available data from a distribution circuit together into a single place. So for example, many of our electric utilities in California, they have this issue that they spent a lot of money on smart meters. And the smart meter data, well, first of all, they're not really measuring everything that you would like to know, or they're not communicating it all back. Like, they measure voltage, but they don't tell you the voltage. You know, if we could only get those data to the control operator, that would have been really helpful. But then also the data go to the billing department, right? Because that's what it was designed to do. At the time they were designing these smart meter systems, they weren't thinking about a whole different paradigm of operating distribution systems. So, you know, even getting the meter data out of the high security vaults from the billing department into the same room where the engineer is sitting trying to do power flow calculations is really tricky, right? But so, having said all that, let's look at some of the actual technology. So this is an example of basically illustrating the relationship here with the phase angles that I described. So the red graph, so this is from our project, actual measurements on a circuit that has a pretty large, a 7 megawatt solar photovoltaic facility and some load that we don't measure. So the red curve measures the difference in the voltage phase angle between the substation and the place where the point of common coupling where the solar photovoltaic plant interconnects. And you can see, if you can axis, that ranges from somewhere around -1 degree to +1 degree. So that's our entire range, and that's for a lot of power flow. That's several megawatts. And our micro PMU at the two, it's basically measuring the precise timing at the two locations and then taking the difference of the angles. So it's measuring very precisely how that angle tracks. And as you can see, that's nearly the same, not exactly the same, but at least correlated with the blue curve, which is in amperes. That is measuring the current that is injected by the solar PV. The relationship would be a little better if we were showing the net current, which we're not showing, but at least you can get sort of the picture of what, this really illustrates how small the signal is that we're looking at. You know, 0.1 degree is 4.6 microseconds at 60 hertz. So there are a couple of other characteristics of the micro-PMU data that I want to highlight. And one of them that's been found really important by the electric utilities we have worked with, and we've worked with about 6 different utility companies in the US, is simply being able to detect events that otherwise they have no way of knowing they happened. So for example, you might have current spikes that could be due to a very large motor start, or they could be due to a fault. And it could be a high impedance fault that is drawing just enough current to make this big spike, but not enough to actually trip a protective device. And usually that wouldn't actually hurt anything, except as a distribution operator, you would kind of like to know that this is going on. Also, if you're doing planning and any kind of engineering, you kind of want to know that these current spikes are happening. With your traditional SCADA, supervisory control and data acquisition, which are sort of our standard instrumentation, on a good day, you will have a SCADA sensor somewhere behind the substation. That's, some circuits don't have anything. They're basically waiting for a customer to call and complain and say, hey, our voltage seems something's wrong. And then they know that something's wrong, otherwise they have no idea. But even with SCADA installed, the SCADA measurements are these blue dots. So in this particular example, every so many seconds, every 2 seconds, this is actually good SCADA data, every 2 seconds, you have a blue dot. And it just shows that, well, sometime in the afternoon at about 13:50, the current stepped up. But you have no idea that what actually happened in between was this big current spike to 800 amps. That may or may not be something you want to worry about. So with the micro-PMUs, we're able to capture that transient. Oscillations were really the prime motivation for PMUs in the transmission system, because when you think about what's going to cause really wide area outages, it is going to be wide area power oscillations and generators tripping offline, cascading failures because you exceeded some relay setting. And so this is just an illustration that we can measure those kinds of oscillations. This is one utility that I won't name, but they asked us to install micro-PMUs at their very large generator that was having some issues, and we helped them diagnose their issues. Actually, part of our non-disclosure agreement never really accounted for the issues. I can't even tell you what the issues are, except that the utility is very happy that they now know and can take care of them. It was not something they wanted to publicize at all, but what's interesting here is that on this graph you're seeing 1 minute. So you see the oscillations over a course of a few seconds. With the micro-PMU data and the Berkeley tree database that I'll get to in a moment, we are able to zoom in and see the data at really high resolution. So this is zoomed in to the full resolution of 120 samples per second. So it's 2 dots for every AC cycle. Anything faster than that, and it doesn't make sense to report a phasor, because a phasor is a quantity that only is defined in the context of the 60 cycle waveform. So it's really only once or twice, per wave that you can even talk about a phasor. You want to look closer than that, you have to look at the time domain, at the harmonics and the full waveform. But that then gives you information about the local electrical behavior and not about the long distance power flow that happens at the fundamental frequency. So this is really the closest that you can look at AC quantities in a long distance sense. But now, because of the precise timing of this, we're able to line up these data sets very accurately. A few words about what we're using to see this. Most of the good work in academia is being done by under-recognized graduate students. This is no exception. So we have a PhD student, Michael Anderson, at UC Berkeley, whom we basically posed the challenge of, you know, we want to get a lot of high resolution data that's coming at 120 samples per second from several tens of devices, and each one has 12 channels because it's got 3 currents and 3 voltages, magnitude and angle. So that's some terabytes really quick, and we're getting that, and we want to store it all. And we want to access it and zoom in and out, and we don't want to throw any data away because we're researchers and we don't know yet what's actually going to be important. Can you build us a database that will let us look at that? And he said, sure, let me give it a try. So he built us a database that is actually, I think, as big an innovation as is the sensor hardware. So this is just a schematic of micro PMUs talking through wireless modems, or you could plug them right into the Ethernet, talking to the Berkeley tree database or BetterDB cluster, which then stores the data. We don't lose any. We usually don't lose any unless there's some hardware issues. That's another story. But you know, it's different when you're working in a university than in a production environment, and the BetterDB is actually transitioning into sort of a full-scale commercial release. But the BetterDB cluster sends the data to the plotting service, which we can then access. And when I'm through with my slides, I don't want to interrupt it right now, but I can show you actually some live access to the data on the plotter. So what this does is it basically does away with the compromise that people always had to make between the resolution in the data and the ease with which you can access it. Because it's always been true that, you know, if you have really detailed large amounts of data, then it's going to be a pain in the neck to find anything. And it's going to take a lot of work just to drill down into it. We can do extremely fast searches, and I'll tell you in a moment how. And it can also perform online computations of things like the difference between angles here and there, calculating frequency, calculating real and reactive power, or basically any quantity that you, the user, wants to define. And then you can download it for doing analytics with it. And the important thing is, instead of costing an arm and a leg, this is open source code, right? Because that's how we like to work. So the key to having the fast search and finding needles in haystacks is the tree structure of the data, so that basically at any level of resolution, the plotter doesn't have to retrieve all the leaves. It can retrieve the data at a high level of, I don't want to say distillation, there's probably a better word for it. In a sense, it's a summary, right? Because if you look at the data points per pixel at this level of resolution, which is basically showing 2 weeks worth of data, each pixel on the screen includes 263,000 actual 883 measurements, right? So there's a lot of information compressed, but still, for each of these intervals, it's showing you the minimum, maximum, and mean value. So the main line is the mean value, but then it's showing you the minimum and maximum during that pixel interval. So that means as a human or as a machine, very quickly I can say, all right, when did the voltage sag here? We can find voltage sags without digging in too much deeper, but I can then zoom in and say, okay, the voltage sag on February 27th was actually 2, and now we're down to 16,000 data points per pixel, and I can zoom in further and again, I can do this by machine or just as a human visually, and I can find exactly when this voltage sag happened, and by machine this took 1/5 of a second to do, right? The other thing that you get, sort of as a side benefit of making PMU measurements, though it actually requires much less temporal precision, is simply the fact that you can synchronize magnitude measurements. And one of our research findings so far has been that even if you don't use the synchrophasors per se, there's a lot of value and benefit just in having measurements reported from sensors at different places that actually are using the same clock. Because if you try to use SCADA data, our experience with all the utilities that we've talked to is that the clocks are never really set correctly. They're never lined up. So if you wanted to actually look at a disturbance event and ask the question, how did the disturbance event that happened in Northern California get visible in Southern California, you couldn't really line it up because there would be too much noise to pick out the signal and know, well, which of these little spikes is the right one. Well, if you have the time stamping, you know exactly which of the little spikes is the right one, the one that happened at the same cycle, right? So we normally, we're taught to think of voltage magnitude as being a local quantity, but we can actually conceive of voltage magnitude as a long distance quantity, certainly over a few hundred kilometers. And so in this case, there's a voltage sag observed simultaneously at Northern and Southern California locations. And the per unit disturbance is very different in these different locations, but we can still see that it's the same event. And from the comparative magnitude of the disturbance, we can do some triangulation and say, well, where did this originate? Who was closer to the original disturbance? So now I'll go through some examples of practical use cases. Wide area situational awareness, like I said, is really about preventing big outages and seeing how big events propagate. And of course, the classic disturbance event is a frequency drop because somebody dropped the power plant. Or in this case, there's this big DC, high voltage DC line through California. And it failed one day, or the converter station dropped out. So the frequency tanked. And then we can zoom in and see what actually preceded these events. So one big area of interest is being able to anticipate when big disturbances happen, to look at the precursors and see if we can identify risk factors. Or for example, if I had a microgrid and I wanted to make a decision to disconnect and operate as an island because some weird stuff is happening in the big grid and I have maybe some very sensitive and important loads, the idea is I don't have to wait for the disturbance to hit me full on. I get a little bit of warning. So that's an interesting area of research. So another example is high impedance fault detection, which, you know, high impedance faults are notorious for happening all the time, and we don't really have good data about how many squirrels and birds get killed because it just, you know, is a fact of life. But again, sometimes there might be protective measures you can take. So we've been able to diagnose pretty much how many joules it takes to cook a squirrel. But there's also another use case, which is when you have local solar PV plants tripping offline. Sometimes there's a little finger pointing going on about, well, you shouldn't have tripped offline, your inverter was not behaving well. Well, we just tripped offline because your utility system was giving us weird power quality and we're supposed to disconnect by our interconnection agreement, right? So who's right? Well, we can actually see exactly what happened, and this is an example from Southern California where we were able to see that the big inverter that seemed to just be behaving very badly was actually behaving the way it was supposed to, and that it was the palm tree that was making a fault that produced just enough of a voltage sag to get the inverter to trip. So those kinds of forensics are sometimes, you know, if there's a fair bit of money at stake and reliability at stake, it can be really worthwhile for either the owner of the PV plant or for the utility to want to have that knowledge and put the instrumentation in place. Another example of phenomena that weren't really easily visible until now are voltage tap change operations. So these are electromechanical pieces of equipment at transformers that basically they effectively change the turns ratio of a transformer by changing the mechanical connection point of the wires. And they have to do this to adjust the voltage because depending on the customer load, if there's a lot of load and a lot of current, you'll see more voltage drop down the line, so you have to compensate for that. These tap change operations were never really a big deal, except for now, as we begin to see more solar generation on these circuits. There's a lot of concern, especially if you talk to utilities in California or in Hawaii. There's a lot of concern that these voltage regulators are going to get really confused and that they will get worn out from making tap changes up and down all the time, every time a cloud goes by. And they'll break, and they're expensive because they're part of expensive transformers. So it's really worthwhile to have information about how are they actuating. So we can see that. We can recognize and distinguish tap changes from other kinds of step changes. And we have one case so far where we saw an anomaly because we saw this little current signature. That's something you'd never have seen with a different sensor. And that little current, here we see the red line as the voltage measured at the tap changer. The current is the green one as we zoom in. This little anomaly you never would have spotted, and we noticed, and this was just a human looking at it, again, PhD student, looking at the data, going, hey, what's going on here? And we showed this to the utility. They're like, that's really weird. Well, let's go look at this transformer. And they drove out there, and it had a puddle of oil below it, and it was not feeling well at all. And they said, wow, are we glad that you told us this transformer has a problem, because we need to do some maintenance on it, and this would have cost us a lot of money if we hadn't known about it when you just told us about it. So there's a whole field of interest that is predictive health, predictive maintenance for expensive equipment, which I think may actually be one of the use cases that is going to be the earliest to have real economic, punch. If I'm a utility manager and I'm trying to justify this, to my shareholders or to my bosses, the prospect of being able to save some millions of dollars on failed equipment and the reliability impact, that's a big argument. Now, another simple application, and this is really part of model validation. It seems like a no-brainer, but actually, when it comes to phases A, B, and C, most utilities that I know have no idea which customer is actually on A, B, or C. Like, they try to approximately balance it out, but it's approximate. And somebody put a label on some conductors once upon a time that was A, B, or C, but then maybe a storm came and a tree fell over and it got reconnected and whatnot. So most of our colleagues in the US utilities, they're like A, B, or C. But sometimes it would be really good to know, especially if we have customers who want to connect single-phase solar inverters. And if it turns out they're all on phase A together, that's going to cause a much bigger problem than if they're nicely spread out. So, synchrophasors to the rescue, and this is almost too easy a problem to give to the PhD students. Even I, as a professor, can do this. I can look at the data from two different locations, the blue and the red locations, which are both in Northern California. Blue is Berkeley, the Grizzly substation, and red is Power Standards Lab in Alameda. And I can see by finding a disturbance event that the phase that has the lesser disturbance is going to be the same phase, A, B, or C. I can't read the letter, but I can say that they're the same. Now, if I look at the angle, so this previous one was magnitude. If I look at the angle, I can see a really distinctive signature of that disturbance. And I can absolutely say that, the dark red on top goes with the dark blue, third from the bottom, that's the same phase. And then the light blue below that goes with the pink, and the red, the blip goes up, goes with the bright blue, and I can say that's the phase ABC alignment, not rocket science, but I needed a synchrophasor to be able to do that. And this shows the disturbances blown up with the fullest resolution. So that's a pretty simple, but potentially really valuable use case. I'm coming back to this place in California that had the solar injection, and so this is an example that shows a cloudy day and a sunny day. The green is the voltage phase angle difference that we saw earlier. It was red in the other graph, right? Between substation and the solar. And then the blue, same color as before, is the current, the net injection from the solar. And here we also show a brown, which is the net current at the PMU number 1, which is at the substation. So there's a really interesting thing that goes on with the net current of the substation that you wouldn't have known any other way. And it's that it changes direction. So the power flow actually changes direction at the substation, and sometimes this circuit is exporting power through the substation, and sometimes it's importing power and serving loads as usual. And with your conventional SCADA systems, you don't know the difference. You can't tell the difference. This can tell the difference. So you can actually see how the brown curve is sometimes correlated with the green and sometimes anti-correlated. You can see that it's sometimes correlated with the blue and sometimes not. So by looking at the phase angle difference actually crosses 0 about the time that the current reverses. Now what's interesting to note is that the current is not exactly 0 when it reverses, because this is a great test question for power engineering class. Because the inverter is producing at about unity power factor, 0.99, and the load is somewhat inductive, so it draws reactive power, and the reactive power still is used by the load even as the real power changes direction. So there's always some non-zero amount of current. In fact, there's other interesting things happening there, which is that when the current is close to 0, if a tap changer operates, the fact that the load, the customer load, is sensitive to the voltage and responds, as in zip load models, right? Some of it, if the voltage gets stepped down, some of the loads reduce their power demand by different percentage amounts. The upshot on this circuit is that that reduction in load from the tap change down was enough to reverse the whole power flow on the feeder and send it across that line. Again, not something you ever would have known was happening. I won't go into this in much detail except to say that the utility often would like to know how much power is being produced by the solar as well as how much load there is, because all they can see right now is the sum of the two, that is the net power, but they don't know how much load is being masked behind that net power being offset by solar generation. And they would want to know that if they're trying to plan ahead for what if there's a loss of generation because of a disturbance, and then suddenly they're faced with all this load that previously they didn't see. What if they have to do a cold load pickup on that circuit? They don't know how much is behind it. But you might say, well, why don't they just go on the customer premises and put in 2 new meters? Well, because that can be legally kind of tricky. There might be a big fence to climb over to get those meters on, and it's sometimes a lot easier to just make a good inference from the data outside the customer premise. So that's what we did here, trying to see if by looking only at the data from MicroPMU1, we were able to disentangle how much came from solar and how much was load. And then MicroPMU2 was there to keep us honest. That was our control that we checked against. So we basically tried to make the red curve match the black on a sunny day, which was easy, and on a cloudy day, which is hard. This is work by our colleagues at Lawrence Berkeley Lab. So they were tuning some parameters for an algorithm that is not perfect, but it's to within a few % error, which is a lot better than they could do before. So everything I've just shown you in these pictures, I can summarize in text slides, but text slides are not that fun to look at. You guys can keep these slides for reference, and you can go back to them. So I think rather than going through each detailed point here, what would maybe be useful just at a high level to summarize the different applications of interest. So I spoke about state estimation. I think you'll hear a little bit more about that later today. The idea, it's really about trying to squeeze as much knowledge out of a small number of really good data points, right? A small number of sensors with very precise, accurate, and high resolution data. Topology detection is about seeing whether switches are in fact opened or closed, which historically you didn't know until you send the guy in the truck to go out and look. Fault location is an important application because especially when cables are underground, you don't want to have to dig everything up to go find where the problem is. Cybersecurity is another sort of different application where we're basically checking the micro-PMU measurements against SCADA measurements to see if they agree, or if there's a red flag that says maybe somebody tampered with the SCADA measurements. And the flag is if there's a discrepancy, you can check for it. I talked about model validation, so there are different aspects of that. What's the phase connectivity? What is the actual impedance between 2 points? How do inverters and machines actually behave? And what are the losses on a circuit? Do the losses agree with what we predict? Or are there things that are unaccounted for, non-technical losses, power theft, or different kinds of connections than what the model says is there? All kinds of disturbance events. This is actually a really fun sort of academic field because there's just so much to do and so much to look for, and it's a place where you can apply machine learning tools to take advantage of the database. So it's being able to classify disturbance events, figuring out where did they originate, what's happening, and ultimately which of them are actual dangerous conditions and which ones are just another day in the life of a distribution system. Characterizing distributed generation. I spoke about disaggregating solar generation, detecting reverse power flow, also understanding how loads respond to different conditions. Ultimately, we'd like to know ahead of time what's going to be the impact on distribution circuits from more distributed generation. Another related topic actually is electric vehicles, because a lot of us are really scratching our heads, what's going to happen if more people get electric cars and plug them in all in the same place? And ultimately how much a distribution feeder can accommodate of these newer technologies before some upgrades are going to be necessary. My favorite idea, and then I want to retire when I see this work, is to use the phasor measurements to intelligently control resources to play well together. And I think that diagnostics come first, but control, we have some other ongoing research projects to try and articulate how we would use the phasor measurements to make good control recommendations or commands for distributed resources, basically rejecting disturbances and trying to keep things at a nice equilibrium. So for instance, maintaining a steady state phasor difference between 2 points. And you could use control for any number of applications there, including for microgrids and for reconfiguring networks, because oftentimes, for instance, if you want to close a switch between two parts of the network, you don't want to close that switch if there's a big voltage difference between them. So the synchrophasors would allow you, the phasor-based control would allow you in theory to actually get that phasor difference to 0 before you close the switch, and then it's very smooth and seamless. So coming back to, so that was kind of the whole background introduction as to why is this technology important, and so what are we doing with it? We're having a lot of fun with it. We are looking at a number of these applications from the big menu that I just showed you, and our graduate students are working on applying different analytic techniques to micro PMU data for some of these different applications, basically building tools that we hope will become useful in practice sooner rather than later. I'm not going to go down the list except to say that again there's, it ranges from a pretty straightforward inspection of the data to some pretty sophisticated mathematical tools, wavelet transforms, looking, dissecting in the time domain, data and how disturbances propagate, sometimes finding simple correlations, sometimes applying statistics. So it's a pretty rich field, I think, for every single PhD student to find something that they're passionate about and where they can actually make a contribution. I put the little toolbox picture there because what's important to me is that we don't just have, one tool and, the proverbial, if all you have is a hammer, then every problem is going to look like a nail. We don't want to just go around with one tool and say, this tool will solve everyone's problems. But the idea with this project is really to be flexible and adaptable to see what are the actual needs and what might we learn from the empirical data that says, some approach that we thought was super smart maybe isn't that appropriate to use here. Maybe we should use something different. So there is a lot of work really to be done also with the utility locally, because every utility in the US that we've worked with, they've had different priorities and concerns. So our goal really is to be responsive and say, okay, what matters to you guys? That's going to be, making a difference. And sometimes, with data collection, like I said, models are not perfect. Well, data collection is not perfect either. Even when you have a great device that can collect perfect data, and even if you have a great algorithm for optimally placing that sensor, you might go on location and find, you can't put it there because there's like a fence or a metal roof and it gets in the way, or, some kind of mundane practical concerns that really, in real life, impact your ability to work with high precision data. And so we have to be cognizant of that and sort of always adapt, for instance, our analytic techniques to, well, what is it that's achievable in the real world as opposed to what's achievable in a journal paper, because those are often two different things. So I just wanted to show you, well, I'm sorry that Claire is sitting right on the line, but you'll see her on Skype later. Claire Tomlin, my colleague, who is leading the Project 1 on our side. And that's Michael Anderson on the far left at the bottom. He's the genius who did the Berkeley 2 database. Some of you have met Amity Ostfeld because she was here presenting last workshop. So we have actually a longer list of students who are engaged with the project, but this is kind of our core. And so we've had, just to kind of summarize our activities, we've had several workshops, both here in the Philippines and back at UC Berkeley with students participating. We've worked extensively with a software called GridLab-D that's specifically for power flow modeling in distribution systems. We've had workshop on event analytics, on machine learning, and then on contract theory and game theory, which becomes really important when you start to strategize about how do we get the customers to do the right thing with their loads. We've interacted with the students, some of whose presentations you'll see here later today. We have ongoing one-on-one discussions, working on papers, and so forth. So this has been actually a really enriching experience for us at UC Berkeley to work with the students here and for our students to engage as well. And then actually tomorrow we're going to be having a session on curriculum development and taking the research right away while it's fresh and exciting and we still don't know all the answers yet. That's a great time to turn it into academic curriculum so that there's going to be stuff that the professors don't know and the students get to figure out. So a very high-level summary by these project areas, student research projects, and these are the ones by students here in the Philippines, are looking at a couple of different aspects of this demand-side management, including load forecasting and load clustering for interruptible load programs, incentive design, and then advanced analytics, hierarchical multi-agent based demand-side management with user comfort, that's looking at thermal services. And these groupings are somewhat loose because they really do cross-cut. But most associated with Project 2 are projects on optimal PMU placement, on doing state estimation when you don't have all the data that you wish you had, how do you squeeze the most out of limited sensors, estimating, doing state estimation using voltage sags for protection response, and then more broadly event detection. And then finally, really in the analytics side is the non-technical loss detection, fault detection, and localization. That's actually, I think, one of the harder problems because really the question is how closely can you narrow down the physical location of where a fault or disturbance happened. I am not going to go through these slides in a whole lot of detail either. And again, I think they'll be available to participants. But to show just that in parallel at UC Berkeley, our students and we are working alongside with the students here and trying to apply different techniques to the problem of topology identification. So the idea is that some switches in the network may be open or closed, and you don't know exactly which. You might have a SCADA system that indicates open or closed. That may or may not be correct. And maybe you don't want to send a guy in a truck to drive out there and take a look on location. So if you have these micro PMU measurements, can you use them to make a good inference about the actual open-close status? So it's basically recovering the admittance matrix. That's a mathematical way of saying the same thing. So we are working with some of our data from the United States to try out different techniques. It's a very hard problem, it turns out. Another hard problem, and it's very basic, and one of my PhD students is working on it, is to account for the shift in the measurement that's introduced by the instrument transformer. And this is actually kind of an embarrassing problem. I was very embarrassed to speak about this problem until I gave a talk at the North American Synchrophasor Initiative. And I said, you know, we have these ultra-precise sensors, but the measurement of the medium voltage network is only as good as the transducer that's in between. So what if the transducer is 0.3% error, then my measurement is going to have 0.3% error, which is way worse than the actual micro PMU. And the good news is that that error is stable over time. So we ought to be able to do some very cool regression and use some fancy math that my PhD students know how to do, and recover that error and get it out. And in fact, we can try to use algorithms that take differences before and after, so the error drops out and different things.
Stable over time? How about stable over varying load?
Stable over varying load. Well, that's another problem entirely, because now you're talking about a loaded surface transformer. With the instrument transformer, the error also varies with the burden on the transformer, and that's actually something my PhD student he finally got a hold actually of the guy at General Electric who makes the PT that we're studying to see, what can we find out about the transformer model to figure out exactly how the burden impacts that. Well, I was going to tell you that I was embarrassed about this problem until I gave that talk, and then people at this conference said, we're so glad somebody admitted to this problem, because, there's this problem everywhere with transmission PMUs and nobody's talking about it. I'm like, really? Like, yeah, they're all doing analytics with transmission PMU data, and they have these transformer errors, and they're like not talking about it. So, like, okay, I feel better now, and I also feel that if we have an elegant mathematical way of eliminating that error, or at least reducing it, then that's going to have really broad significance. I mean, you can uninstall the PT or CT and test it in your lab and then reinstall it, but by that time you've spent way too much money, right? This is an example of, the voltage measured at the same bus through different potential transformers, same make and model, shows two different numbers. They track each other very nicely, but it's sort of like one of them has a different ratio, right, than the other. And the difference is not amazing. It's, 10 volts, a few tens of volts on a 7.4 kV base. But, if what you're looking for is a difference in voltage between two nearby points, then it matters. PV variability impacts, that's actually, frankly, one reason that we're really excited about getting data from different continents and different climates, because sunshine in a tropical climate is really different from sunshine in Northern California. And what does it mean for the electrical impacts? So that is, in determining the variability and doing some good statistics on that is another research project. Combining forecasting and state estimation is a project that Roel Dobby is working on, also one of our PhD students at Berkeley, and using good modeling along with the state estimation to basically, again, squeeze the most information out of what you have, none of which is perfect. Decentralized learning and control for the grid essentially comes back to how do you make near optimal decisions when the models that you have of the network are not perfect. And you really want to be able to learn good behaviors in a decentralized fashion. I think Claire will speak more about this. And then dealing with privacy, that's another elephant in the room of how do we assure that different participants on an electric network are all making well-informed decisions without revealing anything that people don't want to see revealed. So I think, kind of summarizing this, aside from the fact that it's really fun to work with our colleagues here at UPD, we have some ulterior motives and strategic interests as well. One of which, like I said, is we want to see data from different places and different continents, because distribution systems are just so diverse, and we just love looking at those different data. But it's also that we, I think, are beginning to build a real momentum globally. And I mentioned NASPE, and some of you might consider participating. I mean, the phone calls are always at a terrible time in your time zone. But the North American Synchrophaser Initiative is a place, it's actually not just North America, but there's a lot of European collaborators, and we have colleagues in Mexico as well, that's really building a nice community, really an academic community that is just learning new stuff about, you know, these grids that some decades ago people thought, oh, everything is kind of already known about them, and we're sort of going into this exciting new phase. So it's, I think there's so much to learn that, unlike some areas in academia where people find like there's competition and turf battles, this turf is so big and so wide open that there are cool problems for all of us to work on, and the more we can collaborate and work together, I think the better we're all going to do. So this is the place where I'm going to transition into talking about the actual micro-PMU device. And I'm extremely fortunate because when we worked with Power Standards Lab, the manufacturer of this device, we were partners on this DOE ARPA-E funded project. And so they developed this based on the PQ3, which is a power quality recorder that is a device that, you know, looks at the waveform in the time domain and says you have, you know, so much harmonics in here, and there's a timestamp that says, you know, when your power did funny things and so forth. And so they basically added a really good GPS receiver to improve the timestamp and turn this into a micro-PMU. So one of the key engineers at Power Standards Lab at the time was Thomas Pua, who happens to have sort of retired from Power Standards Lab and live in this hemisphere. And so it was easy enough for him to come join us, and I'm so happy because, you know, if I ever run into a problem with a micro-PMU, there's one guy that I want to call, and that's Thomas Pua. So I'm like, well, if I'm giving a talk about the micro-PMU and I get hard questions, there's one guy I want to have there to answer hard questions. So I just have 2 more slides, and I'll ask Thomas to come up here and do more show and tell about the micro-PMU. These are just some pictures from installations that we've had with US utilities. And you can see there's a modem there. Yeah, maybe Thomas will show you the different parts of it. Depending on the utility, they want different enclosures or different mounting things. So one of the things that we've done on our project here is to talk about what are going to be the specifications when we work with utility here, what are some of the options they're going to want to see for connecting it, and then for bringing the data from the PMU back to a server that we're going to install here at the university. So this is always more fun when you see the actual hardware in real life, and so Thomas has a micro PMU here, so you can, I'll turn it over to you.